All right. Good day, everyone. You are welcome to Special Medics Online tutorial. And in today's segment, we'll be looking at physics as a subject. So please, before you continue with this video, do well to click on the follow button. If you are watching from our YouTube channel, do well to subscribe to our YouTube channel. If you are watching from our Facebook page, Instagram, any of our social media handle, just do well to like, follow, subscribe, and also share this video because someone out there might be needing this particular video. So we'll be looking at semiconductors as a topic. Before we are going to look at the characteristics of semiconductors. So when I mean characteristics of semiconductors, what are those things you will see in a semiconductor for you to know that this particular substance or this particular solid is a semiconductor? Before we proceed, know this semiconductor, as the name implies, it's semiconductor. It's not a full conductor. You understand? It's half conductor. So it's like an intermediate what? Conductor. So it's actually an object or a solid that is in between a conductor and a non-conductor. You understand? You know that metals are conductors of electricity, good conductors of electricity. Why non-metals? They can't conduct electricity. So when a particular object is in between a metal, which is a conductor, and a non-metal, so it's at the middle. That's what we call what? Semiconductors. They tend to conduct electricity based on some conditions. Do you understand? So hope you can easily differentiate between semiconductors and a conductor. And another characteristic of this semiconductor is that they have what they call valence band and conduction band. So in your examination, when they ask you a question, valence band and conductor band, where are they found? They are mainly found in what? They are mainly found in semiconductors, valence band and conduction band. Conduction, not conductor. Conduction band. So this valence band, which is represented with V, it is the low energy region. The low energy region is the valence band. So why the conduction band is the high energy region. So these are what you need to know for your JAMB examination or your WAEC. So we're only giving you the main point here. So what we should understand is that semiconductors, when we mean semiconductors, we're actually focusing on the pure semiconductors. And most of the pure semiconductors are in group 4 of the periodic table. So group 4 of the periodic table, that's where you get your what? Your pure semiconductors. You understand? Take note of that. Group 4 of the periodic table. No, the modern periodic table is from group 1 to group 18. So in group 4 in the modern periodic table, that's where you get your semiconductors. And a good example of your pure semiconductors or elements that are semiconductors in group 4, a good example is what? Silicon and what? Germanium. Silicon and what? Germanium. So in case you're asking the exam, what are the pure semiconductors? It is silicon and what? Germanium. And they are in which group? They are in group what? Group 4. And they are pure semiconductors. So they can ask you what type of bond is found between the atoms of these pure semiconductors. So what type of bond that are found in this semiconductor? The bond found is a what? Is covalent what? Covalent bond. These are possible examination questions. So the type of bond found in the atoms in these elements that are pure semiconductors are covalent what? Bond. They are called what? Covalent bond. So in that silicon, you can always use that C in silicon to remember. You know, silicon has a C in there. So this C, you can use it to remember that it is what? Covalent. You understand? So take note of that. All right. Now, these semiconductors, as I said before, they are in between a conductor and a what? A semiconductor. So they are in between. You understand? The carriers of current in a semiconductors, the carriers of current. You know, if you are talking about electrolytes, now if they ask you the carriers of current in electrolytes, you say ions are the carriers of current in electrolyte. They ask what is the carriers of current in metals, you say is free mobile electrons. Now the carriers of current in a semiconductor, that's Xc, they are what? Electrons. They are electrons and what? Electrons and what? Holes. The electrons is the negative and the holes is the what? Is the positive terminal. Like when you have the electrons, they are negatively charged while the holes are positively charged. You understand? So take note again. If you ask in the exam, the carriers of current in, let's say, C of current, C is the current, carriers of what? Current. If it's in electrolyte, it is what? Ions. It is what? Ions. So the carriers of current in metals, the carriers of current in metals is what? The carriers of current in metals is what? Is free mobile what? Electrons. Free mobile what? Electrons. You see it now. Then if you talk about a semiconductor, I already made mention of it. In the semiconductor is electrons and what? Holes. The electrons is negative now. Holes should be what? The positive terminal. You understand? So what's the name for a pure semiconductor? A pure semiconductor is called what? An intrinsic semiconductor. So when you hear the word pure semiconductor, a pure semiconductor is called what? An intrinsic. So if a pure semiconductor is called an intrinsic semiconductor, it simply means semiconductors which are not pure will be called what? Extrinsic semiconductors. So impure semiconductors are called what? Extrinsic semiconductors. So when you talk about impure semiconductors, they are called what? Extrinsic. They are called what? Extrinsic. They are impure semiconductors. So, but naturally, the pure semiconductors are intrinsic semiconductors. And these pure semiconductors, they will conduct electricity when a battery is connected across its terminal. You understand? So an intrinsic semiconductor, they will conduct what? Electricity. When you conduct a battery, when you take a battery, connect the battery across its terminal, because it has electron and hole movement. So take note of that. You can easily make an extrinsic semiconductor to conduct electricity when the battery is connected across its what? Its terminal. So I talked about impurities. I talked about impure semiconductors. You understand? So, you know, there's something they call doping. There's something they call what? Doping of semiconductors. Now, when you dope a semiconductor, it means you're adding impurity to a pure semiconductor. So when you take impurity, you add it to a pure semiconductor. This impurity are elements in another group that are not in group 4. So when you take elements that are not in group 4, and you add them to a pure or intrinsic semiconductor, you know, intrinsic semiconductor is a pure semiconductor. That's what we call what? Doping. That's what we call what? Doping. The process is called what? Doping. You understand? So in this doping, you are adding an impure, or you're adding impurities. There's the word impurities. So when impurities are added to a pure semiconductor, you call it what? Doping. And that semiconductor will now be called, remember I told you, when a semiconductor is now impure, it's called what? An extrinsic what? Semiconductor, because it's no longer pure again. You understand? So most times these impurities you are adding to a pure semiconductor, these impurities, they are either trivalent or pentavalent element. They are what? Trivalent, the one in group 3, or pentavalent, the one in group what? 5. It's very easy. Tri is 3 now, penta is 5. So it means 3 valence electron in that amount group 3. 5 less electron, group 5. You understand? Because the number of electrons in the outermost shell of an atom will determine the group number. So that is how we get what? An extrinsic semiconductor. When you add either trivalent metal, that's trivalent element, when you add trivalent element or pentavalent element, you add it to a pure semiconductor. And that semiconductor now forms an impure semiconductor. An impure semiconductor is what we call what? An extrinsic semiconductor. The process is known as what we call what? Doping. You know what? Doping. You understand? You know, let me tell you something. You know, trivalent, that's group 3. They are like positive metals. You understand? Then this pentavalent, they are like negative elements, like non-metals. You understand? So this trivalent, anytime you add any trivalent element, if you take the trivalent element now you add it to a pure semiconductor, that pure semiconductor will be called a what? A p-type. That pure semiconductor now is now impure, so it will now be called a p-type semiconductor. You understand? Then if you add a pentavalent element, you know pentavalent is negative. So when you add it to a pure semiconductor, that pure semiconductor will now change to an impure semiconductor. You now get what? A n-type semiconductor. So it's like this. If you take an intrinsic semiconductor, that is I, you add a trivalent metal or trivalent element, you will get a what? A p-type semiconductor. If you take an intrinsic semiconductor, you add a pentavalent element, you are going to get a what? A n-type, because that pentavalent is negative. You have a n-type semiconductor. So that is what we are trying to say here. Is that clear? All right. Now, there's something we need to understand in terms of how temperature affects semiconductors. How does temperature actually affect semiconductor? Remember, if for metals that are good conductor, the resistance is directly proportional to the temperature. You understand? You know what is resistance? Resistance is the opposition to the flow of current. Resistance is the opposition to the flow of what? To the flow of current. So, yeah, if the resistance is increasing, it means the current that will flow will be very small. Do you understand? So when resistance is directly proportional to temperature, in physics, when two quantities are directly proportional to each other, as one of the quantities increasing, when two quantities are directly proportional to each other, as one of the quantities increasing, the other quantity will also increase. I've already explained what resistance is as the opposition to the flow of current. So if you increase the temperature here, anything you do to this temperature, same thing is going to happen to the resistance, because they are directly proportional. So in metals, when you increase the temperature, you are increasing the resistance. You understand? So as you increase the resistance, what do you think is going to happen to the current? Yes, you got that. The current that is flowing will be limited to reduce the inflow of current. So the metal will find it very difficult to conduct electricity. So anytime the temperature is increasing, the conductivity of the metal is decreasing. Do you understand? You see the way we related it. But if it's a semiconductor, the resistance is inversely proportional to the temperature. So if the temperature is increasing, the resistance will decrease. So that means the conductivity of a semiconductor will increase as the temperature is increasing. Do you see the relation here? Because when something is inversely proportional, as one quantity is increasing, the other quantity will decrease. So semiconductors, the resistance of a semiconductor is inversely proportional to the temperature. So as you increase the temperature, you decrease the resistance. As you decrease the resistance, more current will be flowing. There's nothing holding the current again. So as more current is flowing, there's no limitation. The conductivity of that semiconductor is increasing. You see the way we relate it now. All right, so that is it. So let's take a look at, remember we made mention of trivalent elements and pentavalent elements. So what are examples of those trivalent elements? Examples of trivalent elements, those in group 3. So we have aluminium, you can easily know them, aluminium, boron is there. We have indium, all these are examples. Gallium and thallium, all these are examples of trivalent elements. So what about the pentavalent elements? The pentavalent elements, we have for the pentavalent elements, we have the arsenic, antimony, bismuth, and phosphorus. So these are good examples of the pentavalent element. Bismuth and what? And phosphorus. So that is it. Very, very easy. You can, if you know the trivalent elements, if you know boron, aluminium, indium, gallium, and thallium, anyone that is not among these trivalents, now you know they are what? Pentavalent. You understand? So this is it for the catalysis of semiconductors. Make sure you drop your comment if you gain value for while watching this video. Do well to subscribe to our channel, like, follow any of our social media platform, and do well to share to your friends as well. So anticipate for the part 2 of our semiconductor lectures in the next video. Thank you very much.